Welcome, ladies and gentlemen. I'm Alireza Alizadeh, and this is CS Internship. Today, we're gonna go over the step 5 of CS Internship and go over the technical material that was provided in this step and see what we can do with it, what we can achieve with these new pieces of knowledge that we have attained, and just have a bit of fun with data, to be honest with you. Okay, so this step mainly is about three different libraries. First of all, you have NumPy. So you have NumPy over here. Then you have Pandas. Great name, by the way. Not descriptive enough, I think, but I love pandas. Who doesn't? And the last one is Matplot. So Matplotlib. So, what are these libraries? Why do we use them? The first one, as the name suggests, has to do something with numbers, right? But that doesn't really narrow it down because programming is essentially working with numbers. So this one is going to handle our math and algebra. So math and algebra. Especially linear algebra. So linear. Pandas is for data manipulation. So this one handles data. And Matplotlib, as the name suggests, it has plot in the name, is for visualization. So we're going to do this and use this library for visualization. As I was preparing for this presentation, I was thinking, well, maybe I could go through some documents and maybe I could, show you what, some functions and different stuff and some methods that these libraries have. However, I thought it would be a bit boring to just have no example and have a bunch of code and code snippets from all around the web to show you what these libraries can really do. So I instead decided to show off a bit and use one of my own personal projects. Well, it's not really personal because it's the one I did for my data mining course. So I had a course called data mining, and this is the project I did for that. And I'm going to give you an overview of the project, and then we're going to dive right into it. So overview. Our goal is to build a regression model. The goal is to build a regression model. If I can spell it correctly, hopefully this is correct. So we're going to work with regression. And the inputs of this are going to have some properties, and the output needs to be a certain type or a certain unit. So the data we're working with, the data, is from steel industry. So steel industry energy consumption, right? What we're going to do is build a model that predicts, using regression, the steel industry's energy consumption. The inputs to this model will be date and time, date/time, maybe and time is not a good description of it. So it's either date or time or something like that. And you're gonna have current. So these are the only things that we're gonna have to work with. So we don't have any other thing. So we're gonna dive right into our data and see what we find. What's the property of what are the properties of our data, and work with that. So first of all, you need to import your libraries. Nothing serious, nothing really exciting. Then you can load it using the read CSV function of Pandas, which is Pandas is lovely with working with CSVs and XLSX and stuff like that. It's just any type of data you have, you can load it with Pandas and work with it. So we load our data from CSV and we set the index column to 0, which basically means the first column is going to be our indexing column, which here is a date time kind of situation. And you might ask, well, if you're using date time as an index, how are you going to use it in your model? Well, the answer to that is this particular data has some stuff that are represented twice. So for example, date and time is there, but it's also here. Look at this. Like week status, day of the week, NSM. NSM is seconds after midnight, so basically time of day. So you have other representations of the same data. And here we have like lagging current and leading current power factors, which are essentially the percentage of the current we're using. So it's the same as these two columns, but represented differently and more standardized. But if you recall, we're not going to work with these, we're going to work with the raw data because that's what's asked for from us. Moving on, we have our data now, and we have a bit of a styling issue that my OCD couldn't go past. So we're going to rename a column that doesn't follow the naming convention of other columns. So basically you use rename. df rename is very simple. You use this function, you use the keyword columns, and you name the column you want to rename to its final name. So it's going to be replacing this one over here, and it does that. It's very simple and it's very lovely. It's very effortless. After that, we get a bit serious. We need to explore our data. So every time you are presented with a big database, this is not a big database in like terms of production databases. This is a big database if you want to work solo on like your own computer with your own resources and you don't have access to servers and such. To explore our data, we have df describe. So we have df dot describe, which is from Pandas. df describe basically gives you all the metrics that usually in mathematics and like in statistics we need to calculate to get a rough idea of the density of our data, of the range of our data, and stuff like that. So it's going to give us density and range. Density and range. And you can see here it gives you quartiles and it gives you min, max, standard deviation, it gives you average, and it gives you count. So you have all this data, which is going to be essential for you to analyze your data. So quartiles are extremely important for outlier analysis. So what kind of data we have that is an outlier. Moving on. After this, we're going to check that if we have any null values in our data. So dealing with null values, it's its own thing, kind of. Thankfully, using isNull, you can count, and sum, you can count all the null entries in your data set and your database. So thankfully, we don't have any. We can just move past this and not worry about it, which is really lovely. And dfinfo gives you information about data types, non-null count, and columns. So you have 10 columns over here. Most of them are numbers, but some are not. These are problematic. So this is a problem over here. For a matter of fact, load type itself might be the output of another classification algorithm that runs on the same numbers and classifies that day's load as, heavy, medium, or, low, or whatever you want to call it. So we have to deal with these in the futures. But before dealing with that, we need to deal with outliers. Sometimes data gets messed up for whatever reason. Maybe you have a faulty sensor, maybe that day you have a, power outage, and, you have some anomalies in your data. We're going to detect those anomalies. So anomalies. These are not necessarily bad, but you need to be aware of them. Moving on. To do outlier analysis, you need inner quartile range, and it's a tongue twister. Try to say it, 5 times in a row. And for that, you use the quantile method in Pandas, which basically allows you to calculate any type of quantile that you want, which in our case is just the same as quartiles. So basically, the point in which 25% or less of our data lies, and the point at which 75% of our data lies, to the left of it in a graph. So if this is our graph, this is our Q3, 75% of our data, 75% of our data is going to be over here. So this is going to be our 70% of our data. After you get these numbers, you can filter and you can plot to visualize data that lies, outside this realm. So basically, look at this. We're going to use our visualization techniques for now. First of all, a histogram to give you an idea of the density of your data and where it's most dense based on usage, because this is the one we're gonna predict, right? We see, between 0 and 10, it's the most dense area, but these are not like low data points, like 2.5K is still a lot. So this gives you the rough idea with a histogram plot that how your data is basically laid out. Because sometimes when you do like dot plots and stuff like that, as we're gonna see right now, say this is a dot plot. This is not gonna really give you much of an insight because it's so dense over here and here. But with the histogram, you get a better idea. And you see sometimes, stuff like this, which is intriguing. Like, what is this? Why are they so far away from the rest? These are the exact outliers that we're gonna analyze. So to analyze them, we're gonna overlay this using Matplotlib. In this case, SNS. SNS is Seaborn, by the way. Seaborn. It's a library built on top of Matplotlib. So this is basically Matplot, if you want to, oversimplify it. Right here, we have the whiskers and the quarters that we calculated. And you see that outside this main range that we have here, we have some outliers. What do we do with them? Do we get rid of them? Do we keep them? Is it good to keep them? Is it not good to keep them? Sometimes these throw off your model. But here is an exception, in my opinion, because if you look at it and analyze it more deeply, as we have done here with a simple filter on our data frame, which basically means filter the usage if it's upper than the limits that we have calculated, or lower than the limits that we calculated, just show me how it behaves and describe that for me. Do you remember the df describe that we talked about? We're going to use it again here. So when we describe it, we see in comparison to the data below, this is our inner quartiles. So basically data is that not potentially out of bounds and an outlier. And this is our outliers. We see that, okay, the deviation is different, but excuse me, I confused the two tables. This is for our outliers. So you see that max is higher, deviation is less, min is higher. So it feels like they have their own logic and there is a method to their madness. It's not just outliers. So I decided to keep the data, and partially because of that, and partially because they're on less than 1% of our data. So it's not going to be as detrimental to our model to keep 1% of outliers, even if they are outliers, which in this case, in my opinion, it's not. It's valid data, you should keep it, because even though it's higher value than your usual data, it also has higher factors contributing to it. Now, if you remember correctly, we talked about some data types that were objects and not numbers. To get rid of these objects, that's a horrible Jesus Christ. So to get rid of these objects, you can use get dummies. Get dummies, what it does, it basically gets categorical data that we have and turns it into binary data. One of the most useful functions and methods that I have ever encountered in Pandas, it's get dummies. So it basically gets binary data for our categorical data. And from here on out, you can get rid of the stuff that are not necessary or represented in other ways. So for example, week status. I mean, yeah, Saturdays, Sundays, weekends, we know which days are weekends. We don't need a column to tell us that. Or for example, load type. We talked about this might be, a classification algorithm running on the data. So we get rid of this too, because we don't need it. The data is there in raw form. So, and we also remove power factors, not because they're not useful, because also they can be derived from, reactive power and leading and lagging respectively. And partly because we wanted our model to work based on, raw data, not, percentages basically. After removing that, these are just previews of your data frame. That's why I'm skipping them. You get to something that's called a correlation analysis. This is where we get out of scope from CS internship. This is a bit, extreme for this type of CS internship, but I'm going to share it with you because it helps to talk about the importance of visualization and the importance and the power that these libraries specifically give you. So look at this. To get a Pearson correlation, which is a linear correlation factor, so a linear correlation basically means if X goes up, does Y go up the same amount? Does it or does it go down? Both are valuable information. It becomes, less valuable when there is not much of a connection between them. So you get like numbers that are extremely low or, close to zero and stuff like that. But to get all these complex ideas and transform them into Python, you just use .core, .core, which calculates all the correlations and gives you this beautiful heap map that gives you an idea, okay, so lagging current is in touch with usage, which is the parameter that we're trying to predict, etc., etc. And it just gives you an idea of what kind of a relationship your columns and your data points have with each other. After that, we're going to build our models of regression. We touched upon regression in the beginning of the video. What is regression? Basically speaking, you're trying to, in this case, which we are working with linear regression, find a line that is close to your data points as it can be. So for example, this is our line, these are our data points. We're trying to find this particular line. And regression has other models. It's not just linear. You can do multiple types of regression. Linear regression has itself like 4 different types. And we're going to do this, and we're going to do this with cross-validation and k-fold, in this case, tenfold. So this is we're going to be working with tenfold. And I don't know if I should go deeper into tenfold. I think I might. Let's see how it goes. So the idea is we're going to build this, and this goes into scikit-learn. So it's a bit advanced, and it parts away from NumPy and Pandas. I'm not going to talk about these because they're not in the scope of our step, but I'm going to talk about regression, and I'm going to talk about linear regression and why do we do it and why do we have different models of it. So let's skip this big chunk of code. All of these have been calculated and, well, not calculated. It's better to say trained, I think, in this case. Although calculated is not wrong. You can calculate it, regression equation. So tenfold, what it does, which these models are trained on, it basically creates partitions in your data. In this case, 10 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And it chooses one. So for example, it chooses one of them, trains on this, and tests on the rest. So these are our tests. And it moves the train set to this one, then to this one, then to this one, and chooses the best model in the end. Why do we do this? Because sometimes data is laid out in a way that you might get lucky and get a better train set if you're just doing some random stuff. But after this, we see that our accuracy in models are 98, 98, 88, and 88. So you might ask, why do we need the 88 models if we have 98? Well, this is where Matplotlib kind of rescues us. So what we're going to do is plot our models and see how they work and how the predictions work. And as you can see here, after plotting, I'm using subplots here to just accumulate all our plots in one. So a 2x2 subplot, as you can see here, and basically giving my models a bunch of data and saying, okay, predict and see how different you are from the actual values, and then plotting them. So this is the outcome. These are our 98% models over here. So these are 98, 98. And the ones down here are 88. So why do we need these if we have these? A train of thought and my reasoning goes like this. When you look at the plot, as you can see here, we have some very bad predictions over here. By the way, this green line is the perfect, like if it's the same predicted value as the actual value, it's the green line. And we have these very scary stuff over here. When predicted value, which is here, is near 0, okay, but our actual value is like 140. That's a hell of a difference if you think about it. And when you have a company where you have a still industry, your domain expert might come and say to you that, hey, look, it's okay if the model is not accurate in as like 98%. I don't want to have to deal with these. If I predict that we are going to use like 10 kilowatts per hour and it ends up being 140, it's a disaster for us. We can't deal with that. So what do? You give them these models. Look at them. Yes, they're not as accurate. You can see they're not as accurate, but they don't have those crazy predictions. You have empty, predictions for those crazy predictions where actual value and our predicted value contradicts so much that it's like could be a problem for a company. So this concludes our presentation and what we use basically with very simple tools. If you think about it, we didn't use much of NumPy anyway. We made use of Matplotlib to a great extent, and we use Pandas to prepare our data and build our models. We skipped the building of the model because it was out of scope, but this is it. This is basically an intro and an idea of what you can do with the things that you learn in this step. If you have any questions, I'm here, and type it in the chat. We can talk about it. If not, thank you for watching and have a nice day, night, whatever you're having where you live. Yeah.